Good day. I am here to discuss our topic on sound under force, motion, and energy. Let us recall what you've learned when you were in grade 7 about sound. So get your notebook and write your answer on the following statements. Feel free to pause this video in order to prepare your notebook and your pen. So let's start with the first concept you learned in grade 7 sound. The distance from one compression or rarefaction to the next compression or rarefaction is called wavelength. So we were able to discuss last time that the unit of wavelength is meter, and it is the distance from one compression to another compression, one rarefaction to another rarefaction. What do you call the number of compressions or rarefactions passing by a certain point in 1 second? It is called frequency. So the number of vibrations or the number of compressions, the number of rarefactions passing at certain point per second is called frequency. Next, multiplying wavelength by frequency, you will get the answer is speed or velocity of sound. Next, the highness or lowness of sound is called pitch. Okay, our voices are classified based on the pitch that it will produce. Next, the measure of intensity or amount of energy of a sound is called loudness. Okay, so what quantity of sound is related to loudness? It is also called the size of the vibration of sound. Amplitude. So the higher the amplitude, the louder the sound is. Now let's proceed to the wrong ideas about sound. First, sound can be produced without using any material objects. Later, you will know that sound requires a medium in order for it to propagate. Next, hitting an object harder changes the pitch of the sound produced. So the pitch of a material or the pitch of a sound is not dependent on how hard you strike the object. Like for instance, if you are using a tuning fork, the tuning fork have fixed frequency, fixed pitch. So no matter how hard you try to hit the tuning fork, it will always produce the same pitch. Sound can travel through an empty space like a vacuum. Sound cannot travel through an empty space because it requires a medium. Sound cannot travel through liquids and solids. Liquids and solids are good media for sound to propagate. Sound travels slower in less dense medium, and the greater density of the medium, the faster the sound is transmitted. As we discussed, you will be able to unlock these misconceptions. Okay, look at the illustration. Which illustration correctly describes how sound is propagated between the source of sound, like for instance the speaker, and the receiver of sound, like the human ear? Letter A, letter B, letter C. This question was given to grade 8 students during the international PRISM test, PISA test given to grade 8 students. So your answer is, so the correct answer should be letter A. So sound travels through expansion or rarefaction and compression of air particles. Okay? So when particles of air vibrate, they collide with one another, causing compression and rarefactions. Now, these compressions and rarefactions transfer energy from one particle to another until the energy in the form of sound reaches the ear. For this particular week, we need to answer these key questions. On which medium does sound travel fastest? Solid, liquid, or gas? How does the temperature of the medium affect the speed of sound? And how are reflection and refraction manifested in sound? Hopefully, at the end of this discussion, you will be able to answer these questions. Let us recall on waves. Let us have a recall on waves. So when you were in grade 7, you discussed that there are two types of waves, the longitudinal wave and the transverse wave. If you will be using a slinky to represent longitudinal wave, you are going to move the slinky forward and backward to produce a longitudinal wave. So the coils move left, right, to produce a longitudinal wave. You will see that as the spring or the coils move left and right, energy is transmitted. While for transverse wave, the source moves up and down, and the coils move up and down. As the coils move up and down, energy is transported. So these are the differences between longitudinal wave and transverse wave. Another example, if you will be considering the particles of a transverse wave, you will see that the particle moves up and down as the wave propagates from left to right. While in longitudinal wave, the particles move sideways as the wave moves forward. Okay? So in terms of the characteristics of waves, let us differentiate the different characteristics of waves. So for longitudinal wave, you have the compression and you have the rarefaction. The distance from one compression to another compression is called wavelength. Okay? And then, the distance between the equilibrium position and the rarefaction or the compression is called the amplitude. While for transverse wave, we have the highest point as the crest, the lowest point as the trough, and the distance or the height between the equilibrium position and the crest or the equilibrium position and the trough is called amplitude. And the length or the distance from one crest to another crest is called wavelength. One trough to another trough is also wavelength. One point to the next corresponding point is called wavelength. Okay? So, for the amplitude of a longitudinal wave, we look at how compressed or how rarefied the springs or particles are. The more compressed or the more rarefied it is, the higher the amplitude. The less compressed and the less rarefied, the lower the amplitude. Okay? So these are another differences between longitudinal and transverse. Okay? One good example of longitudinal wave is the sound wave. While for transverse wave, one good example is the visible light. We already discussed this when you were in grade 7. When you were in grade 7, you also computed for the speed of a wave. So the symbol for the speed of the wave is V, and it is equivalent to lambda times F. Lambda is the symbol for wavelength, while F is the symbol for frequency. So the unit of wavelength is meter, the unit of frequency is hertz or per second. So meter times per second will give you a unit of meter per second, which is the unit of speed. Another equation for speed is wavelength over period. Wavelength is in meter, period is in second. So wavelength divided by period is meter divided by second. So the unit of speed is meter per second. We already solved similar problems to when you were in grade 7. So when you were in grade 7, you computed for the speed of a sound wave. Suppose the wavelength is 3 meters and the period is 30 seconds. So what is the speed of the sound? So the formula is V is equal to wavelength or lambda over period. So 3 meter divided by 30 seconds will give you 0.1 meter per second. So 3 meter divided by 30 seconds will give you 0.1 meter per second. Another, suppose the wavelength is 5 meter and the period is 45 seconds. So 5 meter divided by 45 seconds will give you 0.11 meter per second. When you were in grade 7, we computed for the speed of sound. So this is just a review of our problem-solving activities when you were in grade 7. Now, let us discuss in detail the characteristics of sound. What is the source of sound? When you were in grade 7, we already discussed the source of sound. The source of a sound is a vibrating object. So whenever an object vibrates, sound is produced. Like what is given on the screen. A tuning fork that is vibrating and a cymbal that is also vibrating, producing sound. How does sound propagate? So sound is transmitted when particles collide, producing expansion and compression. Take note, sound is transmitted when particles collide, producing expansion and compression, similar to this one. One good example of how sound travels from the speaker to the receiver or to the human ear. So you will see that the air molecules collide with each other, producing compression and expansion or rarefactions. So as there are compressions and rarefactions, sound is transmitted. Okay, this is another representation. So sound consists of waves of air particles. Sound needs a medium to propagate. That is why sound is considered a mechanical wave, because a mechanical wave requires a medium to be transmitted. Sound is characterized as longitudinal waves because sound travels through compressions and rarefactions along the direction of the pushing and pulling activity of the material or the medium. Where does sound travel fastest? So I have here a simulation of how sound travels in solid, liquid, and gas. So suppose that the air particles are represented by domino. Okay, dominoes. So the black part represents the source of sound. As the sound reaches the first domino, energy is transmitted. So you will see that sound travels fastest in solids, followed by liquids, and then gases. What are the characteristics of solids, liquids, and gases that allow sound to travel? So solid solid material have a very close intermolecular spacing, while liquid has slightly farther intermolecular spacing, while gas is far from one another. In terms of volume, solid has definite shape, while liquid takes the shape of the container as well as the gas. Solid cannot flow, while liquid and gas can flow. Solid is not compressible. Liquid is also not compressible, while gas is highly compressible. Solid is densest, followed by liquid, and last, gas. These characteristics of solids, liquids, and gases allow sound to travel through them. So these are the factors that affect the speed of sound. Number 1, elastic property, or the ability to maintain its shape and not deform when a force is applied to the object or medium. Example of elastic materials are iron, copper. In terms of insulators, we have rubber band. So they are considered elastic material. So particles that quickly return to their rest position or to their initial shape can vibrate at higher speeds. So sound travels faster in medium with higher elastic properties. Among solids, the most rigid would transmit sound faster. Next, density. Density pertains to the bond strength between particles. So bond strength between particles is strongest in solid materials and weakest in gases. Sound travels fastest in solids and poorest in gases. However, if a material is denser because its molecules are larger, it will transmit sound slower. So even if a material is denser compared to another material, however its particles are larger, it will transmit sound slower. And sound will travel at a slower rate in the more dense object if they have the same elastic properties. So if solid materials have the same elastic properties, a denser solid will allow sound to travel at a slower rate. Now, I have here pictures of how sound travels from the source to the receiver. Like for instance, a mother placing a headphone on her womb in order for classical music to be heard by her baby. How the sound travels from, how does the sound travel rather from the headphone to the ears of the baby in the mother's womb? Another, a person spying by listening to the conversation in the other room through the door. How is sound transmitted? And another one, a tenant who cannot sleep because of the noise from the other room. So these pictures are part of your activity 4.1. So you need to explain how sound travels from the source to the receiver and what medium is used for the sound to propagate. Aside from elastic properties and density, there is another factor that affects the speed of light. Sorry, not speed of light, speed of sound, temperature. So temperature is the measure of the average kinetic energy of a material. So high-speed particles have high kinetic energy, thus producing high temperature. So when particles move fast, they possess high kinetic energy. So their temperature is also higher. So how is temperature related to the speed of sound? So as temperature increases, the particles vibrate more. So when particles vibrate more, the pitch increases. As the pitch increases, there are more vibrations, there are more compressions, rarefactions per time interval, frequency increases. And we were able to identify that frequency is directly proportional to speed. So the higher the frequency, the higher the speed. So as the temperature increases, the speed of sound also increases. So the relationship is direct or direct proportionality. How do we represent this relationship in terms of mathematical equation? So the equation for speed of sound is 331 meter per second plus 0.6 meter per second per degree Celsius times temperature. It was observed by scientists that per degree increase, per 1 degree Celsius increase in the temperature of air, there is a 0.6 meter per second increase in the speed of sound. So V is the speed of sound. 331 meter per second is the speed of sound in dry air at 0 degrees Celsius. And T is the temperature of the medium at degree Celsius. Let us try to solve one problem on how to compute for the speed of sound given the temperature. What is the speed of sound at 10 degrees Celsius? So, you need to write the formula because in activity 4.2, you will be asked to solve for the speed of sound. So in order to get three points, you need to write the formula, which is V is equal to 331 meter per second plus 0.6 meter per second per degree Celsius times temperature. Then, you need to substitute. So the temperature, 10 degrees Celsius. So 10 degrees Celsius is substituted to this part. Okay? So since degree Celsius and degree Celsius, so it is in the numerator, this one is in the denominator, so the They can be canceled. Okay? So 0.6 times 10 will give you 6 meter per second. Plus 331 meter per second will give you 337 meter per second at 10 degrees Celsius. So in order to get 3 points in your problem-solving activity, you need to write the formula, the substitution together with the cancellation, and the final answer. Okay? Formula, substitution with cancellation, and final answer. In your previous problem-solving activities, some of you were not able to get a perfect score in the GRESA method because you were not able to cancel units. So you need to show the cancellation of units in order to get a perfect score in the problem-solving activity. Now, let us summarize. How does temperature of the medium affect the speed of sound? The higher the temperature of the medium, the faster the speed of sound. They are directly related. What are the other factors that affect the speed of sound, or what factors affect the speed of sound? The speed of sound is dependent on density, elasticity of the medium, and temperature. Now, let's proceed to another topic. And this is, why do sound waves travel or transmit farther and clearer at night? Is it because it is quieter at night? So these illustrations will be discussed as we go on with our presentation. So is it really correct that sound waves transmit farther and clearer at night because it is quieter? So the previous slide can be answered through one property of light, one property of sound. Okay? And this property of sound is called refraction. When you were in grade 7, I've introduced refraction and reflection. So refraction is the bending of light, is the bending of sound rather. Refraction of sound is the bending of sound when sound enters the boundary between two media. Suppose this is the incident sound. So this is the incident sound, and it crosses the boundary between warm air and cold air. So since warm air has higher temperature, the speed of sound here is fast. While here, since it is cold air, the temperature is low, so the speed of sound will be slower. It will become less. So because of the change in the speed of the sound waves bend or they refract. One good example is when a vehicle sends sound through air, and there is warm air and cold air. So since there is a difference between the temperature of the two region of air, warm air has higher temperature, so the speed of sound will be faster. Cold air has lower temperature, so the speed of sound will be slower. So because of this, the sound waves bend away from the warm region. Take note, as the sound bends, it bends away from the warm region. Since the speed of sound increases in the warm region, so sound waves travel faster. That's why they bend away from the warm region. So when sound propagates in air, where temperature changes with altitude, sound moves faster and bends away from the hotter or warmer region. So this is an example, warm air, cold air. So sound bends away from the warm air. Here, warm air, cold air. So the sound waves bend away from the warm air. So the sound waves always bend away from the warm region towards the cooler region. So during daytime, wherein the ground is hot, so the air above the ground is also warm. So since this region is warmer and the upper region is cooler, so sound travels faster at this region. So sound bends away from the warmer region. So if you are occupying the second floor and someone is talking in the ground floor, you will be able to hear the sound of the person speaking on the person speaking in the ground floor because the sound bends away from the ground. But during nighttime, wherein the ground is cooler, so the air particles above the ground is also cooler. So when sound is generated from the source, it bends towards the ground. Okay? So let us apply the bending of sound in this question. Why do you think open field concerts are usually held during nighttime? Does the speed of sound and its propagation relate to this situation? And take note, the stage of this concert is placed above the audience. The speakers are placed above the audience so that when the sound is produced, it will bend towards the ground. So the audience will be able to hear the sound clearly. Okay? So during open field concerts, you'll be able to see that the speakers, the stage is placed higher than the audience so that when sound is generated, it will bend towards the ground and it will be able to reach the audience ears. Now, aside from refraction, we also have reflection of sound. So, like for instance, the communication between the airplane and the transmitter. So, the airplane will send signals, sound waves to the transmitter, and the transmitter will reflect the sound back to the target, to the airplane. Okay? So, take note, and it can also be that the transmitter emits wave and the target will reflect the wave so that the transmitter will be able to know the distance of the plane from the tower so that they can give information, instructions to the pilot. We know that the pilot is blind when it is driving the airplane because they can only see clouds. No, they are blinded by the clouds. So what will guide them is the instruction from the transmitter or the receiver. And they can help by sending signals or waves. Okay? Take note that the pilot is not blind but blinded by the presence of clouds and turbulence, no? Clouds. The pilot will only see the clouds. They cannot see anything there. So the transmitter will aid them in navigating the airplane so that we can arrive safely to our destination. Another is through ultrasound. So high frequency sound waves are being reflected by the tissue of the baby in the mother's womb so that the image can be seen on the screen. Okay? Another, a ship sends a sonar in order to know the depth of the ocean floor. So as the signal, as the sound waves are transmitted from the ship, it reaches the floor of the ocean and it will bounce back to the ship, and they will be able to measure the time of the return of the sound waves, and using the time, they can measure the depth of the ocean floor. So reflection and refraction play a very important role in the application of sound in our daily lives. To end my session on sound, I have here a question. Why is the moon described as the silent planet? I hope you will be able to answer this. Why the moon is described as the silent planet? Can sound be heard on the moon? That ends my presentation, and hopefully this will help you in answering the supplementary worksheets and the learning tasks in your SLM. Thank you and have a nice week.